Hello, hi, welcome. So today I'm going to be talking to you about how to improve visual rendering quality in VR. So my name's Ryan and I work for Arm. So for those of you who don't know who Arm is the world's leading semiconductor IP design company. So what that means is we basically design chips and processors. So to give you an idea of how wide or how large Arm is, our technology reaches over 70% of the world's global population, and over 95% of the world's smartphones are based on Arm designs. So we're pretty big, and we've been around about 26 years. And so Arm hardware powers a whole range of devices. This goes from smartphones, supercomputers, agricultural sensors, all the way through to servers. So the new Unity server process is also based on Arm chips. So 23 billion Arm Cortex CPUs shipped in 2018, or over 1 billion Arm GPUs shipped just last year. So we're pretty big, and we've been around for a while. So Arm's also been at the forefront of gaming for the last 26 years. And in this time, we've released or powered some of the most iconic devices ever released. Last year, we created this VR demo to showcase just some of the devices we've been involved in. So as you can see here, there's some of the earliest Nokia phones released. And the Panasonic 3DO, you can see kind of disassembled at the front there, which definitely predates me by quite a while. And all the way through to the Nintendo 3DS and DS. And now we're coming into the flagship smartphones available now, as well as the Oculus Quest, which is probably one of the most recent devices with our power. So in this time, we've also produced many VR demos in the last few years, and we've always worked to try and push the most advanced pioneering technologies in our demos. So this was released back in 2017, I think, and this was using foveated rendering, as well as multi-view, which are some of the technologies you see quite commonly today. So it's all designed to demonstrate the depth of experiences available on mobile devices and standalone devices. We frequently work with game developer partners. An example is this demo we produced with Fast Travel Games, where we worked to port their Apex Construct, which is a PS4 VR game, and we worked to port it to mobile. And in the process, we also integrated inside-out camera tracking to provide 6 degrees of freedom, which was definitely a first back in 2017. But now you can commonly find it in the headsets like the Oculus Quest. And as you can see here, we worked really hard to try and keep the same visual parity between console and mobile. So, yeah. So moving on, now you know a little bit about Arm. Here's the current state of VR. So VR allows developers and you guys to deliver new, really deep, immersive experiences that you just couldn't deliver with traditional mediums such as 2D monitors and displays. So this is fantastic for you guys, and it's fantastic for gamers and people enjoying these experiences. But this new method or medium has a number of downsides, and it's limitations in comparison to the traditional mediums. These come from the stereoscopic lenses that you need to get that 3D immersive experience, as well as the player's ability to really get extreme points of view in your scenes. So these limitations have big problems. They can cause people to become nauseous, uncomfortable, and just ruin the whole experience. So you need to overcome, mitigate, or solve all of these limitations to the best of your ability to try and provide the most immersive experience for everyone. So to give an idea of how big standalone VR headsets is, there's been a 2 times uplift in standalone headsets installed bases in the last 2 years. So that's twice as many sold. So this is an area you really need to be targeting. So it's not just about desktop VR or PlayStation VR. You need to be thinking Oculus Quest and those kind of standalone headsets that are coming out. They're great to target. And 38% of all VR headsets sold this year are projected to be standalone devices. They're really catching on with consumers, and you should be definitely focusing on them. So there's 4 main pitfalls we've identified in VR when we've been producing our demos. This is one of the biggest is aliasing. Lots of these VR demos suffer aliasing around the edges of models, inside textures, shaders. There's aliasing everywhere, and it ruins the experience for lots of people. The next up is banding. These kind of darker scenes, they're set this kind of more special tone that you guys want to apply in your art style. It comes with the side effect of huge banding visible in the levels. Next up is depth. The more traditional ways of producing depth inside the scenes just doesn't work so well inside of VR because of the stereoscopic lenses. And finally, the traditional shadow mapping techniques just aren't quite as refined as they need to be in VR, and they come with expensive performance costs. which you just don't have available. So aliasing is resulting from you trying to display your 3D objects on a traditional monitor or on a discrete grid of pixels, and this is where you get this aliasing. Your banding comes from your trying to represent the colors in your scenes onto the number of bits per pixel available in the monitor. And then the depth is coming from this multiple viewing angles and the stereoscopic lenses, these problems. So that, and the shadows is from on the standalone headsets. You have a limited amount of resolution, or you try to decrease the resolution available to try and speed things up, and then you have these poor shadows. So moving on to just how to mitigate these problems. Starting with aliasing, there's a whole range of mitigations available for aliasing, and I'm sure you guys are aware of many of them. So there's the basics, which you guys should always be implementing. There's MIP mapping, which you should have on all the time. There's level of details, and Unity offers you to have object and shader LODs. I know a lot of people have heard of object LODs, but the shader ones are something that's unique to Unity and definitely worth trying out. So for those objects in the distances, you can provide lower resolution, faster shaders to try and speed things up. And then you can also apply anti-aliasing on your standalone headsets. You want to be thinking of MSAA. It's really fast on those tile-based renders that those standalone headsets have. Moving on to texture filtering. Now I'm sure you guys are wondering, why is this not in the basics? Everyone knows about it. It's because it's really complex when you get down to it. There's so many different options and configurations available. You have bilinear, trilinear, anisotropic, 2 times, 4 times, 8 times, 16 times. And you need to be working on a texture by texture, use case by use case basis to work out when to apply which type of texture filtering. And trilinear and anything above 4 times samples is going to be too expensive for those standalone headsets. So you want to think lower. But when you can achieve a lower, you can afford a lower resolution or lower type of, faster type of filtering, definitely give it a shot if you think you can get away with it without sacrificing that visual effect. Then color space. This is a bit of a weird one. Not many people are aware of this. But Unity allows you to switch to linear color space rendering, which isn't the traditional method, but as PBR is becoming more commonplace, lots of people are trying it out. And the good thing about linear rendering in VR is that as you increase the brightness in your scene, the objects don't become overexposed and turn white. If the objects become white, then you get specular highlights, and this ends up with specular aliasing. So try switching to a linear rendering space to see if that reduces some of the specular aliasing in the scene. But be aware, if you do this, you're going to need to retwig your lighting a little, change the intensity, change the range of the lights, because things are going to look different. Be aware of that. So finally, there's a big one, alpha compositing. Right? It's really, really common. But the most common methods, your alpha testing, your alpha blending, they either have a lot of aliasing in them, or you pay for moving objects with alpha blending, not looking so good. So you need to think about how to do this. So I got a bit of an example here. So on the left, you can see an alpha tested bush, and on the right, I got an alpha coverage bush. So this is a bit of a new idea, and I thought I'd give you a, well, it's been around a while, but not many people are aware of it. So as you can see, the bush on the left, as it fades into the distance, it loses its presence in the scene, it disappears. But on the right, with the alpha to coverage, it stays there as it goes into the distance. The leaves don't disappear, it all maintains its presence in the scene. So I'm sure you're wondering how to do this. So we'll go back a bit, and we'll go back to the alpha test. So the alpha test and alpha blend are the most common. I'm sure you guys use all of them, or you have used them, or are well aware of them. So alpha testing produces these rough edges, right? You have this binary, don't shade, do shade, and you end up with these really jagged edges around the edges of your objects. Alpha blending isn't great either. It gives you nice smooth edges, but when you have this moving bush, you don't get the per pixel depth sorting that you would typically in an alpha test shader, so you end up with this incorrectly sorted polygons on your bushes, and then the bush looks inside out. It doesn't look right. So you need to think of a way of solving this and a solution for this. So here comes alpha to coverage. So it's been around a number of years, but if you can look on Google, you'll find the first blog mentions the word esoteric, which gives you an idea that not many people know it really exists. So a possible solution to this in Unity is really easy. You just throw in alpha to mask into your shader at the top, and it automatically enables alpha to coverage for you. And alpha to coverage works by taking the sample or the coverage mask that comes out of your MSAA and then mapping this to the alpha output. So if you have a 0.5 value that comes out of your pixel shader or fragment shader for your alpha, it only renders two of the coverage samples in your scene or object in the MSAA. So that gives you much smoother edges while keeping the fast process that you don't have with the alpha blending. So moving on, I've created a code snippet to show you guys how to implement this. So at the top, you've got alpha to mask. So you just put that on. And then, so you can enable the standard alpha to mask, but this doesn't work quite so well. So you guys need to be trying to expand this a little bit. And there's a few ways to fix some of the issues this throws up, because it doesn't look so good at first implementation. So you've got a fragment shader here where you sample your diffuse texture as normal. And then you work to calculate the common MIP level. This is because as your object fades into the scene, you'll trade down MIP levels inside of your texture, but as you do this, you'll go to lower alpha levels, and then you'll have cutoffs between the alpha that doesn't work quite the same. So to do this, you need to calculate the current MIP level and scale it up so that you have a standard level of MIP coming out of your alpha, which then you can use in your alpha to coverage. Otherwise, you'll get this losing of presence as it fades away, and you lose a progressively smaller alpha channel. Then you need to sharpen your texture to the width of a pixel so that you don't have lots of overlapping pixels on top of each other, which then cause banding, right? So if you just provide a simple F width, I'm sure lots of you have heard of that function, and then you sharpen it appropriately so that all of your alpha texture pixels match the size of a pixel, and then you can use that in your clipping and then carry on with your lighting calculations as normal. This is some simple N.L here at the bottom, and then you return your color. And this is going to give you pretty quick implementation, looks good, much better than alpha test, much better than alpha blend. And to make things better, in Unity 2017, there's an option called Mipmaps Preserve Coverage. So if you go to your texture and you go into the texture inspector, there's an option, just a quick tick box there called Mipmaps Preserve Coverage. And if you click that, you can skip the whole bit about mipmap calculation and to work out the level and scaling it, which brings you down to one level or two lines, alpha to mask and sharpening the texture alpha and then clipping like a normal alpha test shader. This is super easy, not much more performance cost because you can see you're really not doing much more. So if you've got MSA, give this a shot and see how much better your foliage is going to look in your scenes. Then we've got banding, right? So I'm sure you guys have all seen it. You've got a nice dark wall. You've got a cool little scene going on with a really nice ambience. You've got a point light there, maybe a purple point light. And all you can see around the edges is these horrible looking bands of color as it gets further away from the center of the light. So there's two approaches for this. There's dithering and there's tone mapping. So I'll start with dithering. So dithering is the idea you basically apply this kind of disruption pattern into your scene to try to break up these bands. And this stops the eye becoming so attracted to them. Because the real problem with banding is the human eye is drawn to these color changes and these bands, and they stick out a lot to your players. So by dithering in them and just breaking up those patterns just a little, you can really disrupt it, and it pulls, and it stops the eye being so pulled towards it. Next up is tone mapping. When you tone map from the high definition range, high HDR colors to LDR colors, you can remove those sharp gradients of color changes in your screen. And that really helps to stop the bands being so apparent. So this is super easy to implement as well. Unity's post-processing stack v2, as soon as you add a layer and a volume to a camera, it automatically enables dithering on that camera. So there's nothing you need to do other than install the post-processing stack v2 and add a layer and volume. And then for the tone mapping, it's an option right there in the post-processing stack. You can click it, and this is going to be similar to the color space as well. Again, when you change this, things aren't going to look the same as they looked originally. So if you've got an artist, they're going to want to play with the lights again to make things look like they looked before if you want to preserve the original color scheme, which I'm sure you do, because I'm sure your artists have spent many times getting it right. So moving on, I've got an example here. So here's a screenshot of a point light on the black scene that I described previously, and I've brightened it quite a bit and increased the contrast so you can see those bands clearly around the light as it falls off. So while I've artificially brightened it here on the screen in the bright lights, on the inside of a headset, in a VR headset, immersed, those is kind of how they would appear to your player, and especially when your lights adjust to the darkness of that. So this is how it will kind of look. So if I apply dithering and tone mapping, so you can still see these bands around the edge. They're there, they're not completely gone. But if I zoom in now, you can see around the edge, there's a lot of individual pixels scattered around those bands, which are dithering it and breaking up the pattern. This will automatically stop your players' eyes from being drawn towards those bands when they're inside of the VR headset. So again, really easy to implement. Give it a shot, see if it improves things for your players. Moving on to depth, right? So I'm sure you all use normal mapping all the time. It's really cheap. One additional texture fetch, super fast, really looks great. Unity make it super easy to implement. And it provides those additional details during your lighting calculations to help give you additional details on your objects without paying the additional vertex processing cost as you would normally, right? So it's fantastic. Problem is, in VR, it's not quite the same because it doesn't consider the point of view and it has no way to account for those two lenses you have inside of a VR headset. So while it still has an impact and it definitely looks better than a standard diffuse map, you should be trying to think for those textures that are up close to the player that they can move around and look around on. You should really think to try out parallax occlusion mapping. So this is a more advanced method of occlusion mapping, and I give you, it's more expensive, so you need to be considering when to use it, only on those textures that are up close to the player that they'll really see the difference on. So basically, parallax occlusion works by, it's a form of raycasting, right? So you raycast from the eye vector into a height map that you provide. You can bake these out of 3ds Max or whatever your image authoring program is. And then they raycast into this height map, and you can find the exact offset for the texture coordinates relative to the user's point of view into your texture, towards your texture. This way you get texture coordinates that offset correctly, so that when the user's looking at this texture, they look, the objects and all the details look correctly adjusted to look more extreme to the player. So this means as they look from the side and different angles, they can see the texture really sticks out much more than it would if it was just a single diffuse texture. So I've got an example here. Here's a pretty straightforward diffuse texture of some nice cobbles. Nice cobbled stone wall there. And if I flick on normal maps, you can see you've got the additional shadows around the edges of the cobbles, as you would expect. And so just to jump back so you guys can see the difference, there's a few additional cobbles. I'm sure you guys all know it. Looks great on your standard monitor. Kind of falls down on VR though. So moving on, I've got parallax occlusion mapping. Now, it doesn't look great here, but inside a VR headset, when you can move around it and see the different angles, you'll see those rocks really convince you to look like they're sticking out. So Unity enables this inside the standard shader. You can just throw in a height map, increase the height, and there you go, and you'll have it straight away. So you see the difference again. So that where to really look for is on the edges of the rocks that really stick out. They're lit much more obviously and much more brightly on the edges of those objects that are sticking, protruding out more than others. So that's where the real benefits lie. So just to switch back through all of them, here's a diffuse, here's a normal with shadows, and here's a parallax occlusion with that protruding objects really obvious. And then here's a comparison of all three to get you a sense. So moving on. Finally, there's the shadows. So you got your traditional shadows, right? You got your shadow mapping, you've set it up, and it doesn't look so good. You've got some Moya patterns from your shadow artifacts, so then you put in a bias to try and fix it, and now you've got Peter panning, your shadows are offset. It's not looking great. And to make things worse, because you're on a mobile headset, you drop the resolution of your shadow map to try and save on bandwidth, to save on power, as everyone's told you to do, and now you've got this dreadful resolution, super low resolution shadow map, which is really nice and fast, but you've got the problem that there's projective aliasing and there's perspective aliasing. So you gotta stick with it because shadow mapping is vital for that player immersion. Without shadow mapping, things just don't look good. So what do? Well, you can go for the standard blob shadows, right? So this might seem like a really cheap approach. You just throw in a blob shadow and you think this isn't going to do anything. But if you compare a blob shadow to a badly rendered shadow map, it just gives the additional detail on those dynamic objects. If you've got a player running around, you can just put a blob shadow below them, a dynamic one, so if the player jumps, the blob shadow gets larger. As they come closer, it shrinks. And this helps give them a shadow. It's not perfect, it's not pixel perfect, but it's something, and it helps to keep the immersion of the players without blowing out your processing budget, your frame time, and looks good, right? And as a backup for those higher resolution models, those static things or those static objects in your scene, you can bake those shadows in Unity's processing time and just bake the detail and bake the shadow into the texture on the ground for those static objects. So then you have those super high resolution texture. And this way, you're not paying extra for the additional render pass for your light. And so you're saving on your shadows while keeping great looking, highly immersive shadows. So I got a quick example here of comparing a rock on the left with a traditional shadow map and a blob shadow, right? There's really not much between it. I mean, sure, the one on the left looks more, but from this angle, you really can't see much difference between them. And especially in VR, up close, that shadow on the left is going to have a lot more aliasing. You can even see it here around the edges, right? Well, that blob shadow just smoothly fades off. I'm sure you're thinking, this is going to be a nightmare to implement. Well, with the Unity Standard Assets Pack, you can just import it, click on the shadow, go straight to it, turn off Cast Shadows, and then go down, go to your Standard Assets, Effects, Projectors, Prefabs, find the Blob Shadow Projector, literally just drag and drop it on top of your rock, or your object, whatever it is, your player, and then just translate it so that it's above it, and then get it pointing down if you want, and you can have it placing at any angle you want. And then as you see, as you move the individual object, the shadow scales with it as well. And that was 30 seconds, probably less, right? And now you've got really good looking fast shadows that help to provide that immersion without losing on the performance. And this is super worth it, right? Give it a shot. You might be surprised when you come to quality testing or some kind of testing afterwards that your users just think, oh, it's a shadow, right? That's what I need for my immersion. It doesn't break the immersion, so it's better than having a broken shadow or no shadow, and it's super quick to render. Right. So all these effects, you should deploy them on a case-by-case basis, right? Think carefully. Try and deploy as many of these mitigations as possible. But also, as you design your levels, think carefully, right? Try and avoid those hard edges. Try to replace your stairs with ramps. That's going to look better. It's going to avoid those aliasing around the edges. You can try and avoid those thin objects. Don't fill the air with cables. I mean, a place like here is going to look dreadful in VR, so don't try to model it perfectly. As it fades into the distance, all those small struts are just going to disappear, and they're going to flicker in and out and give you loads of temporary aliasing. Players are going to notice it. It's going to be dreadful. Another idea is if you want to keep them, put some fog in, some atmospheric fog. It will hide those distant aliasing objects. So it's really a good idea. Or just put some smoke in. It's another option. You can pre-bake your lighting if you really feel the need for lighting. Pre-bake it, and you get great lighting effects built in offline, and then your scene just doesn't need to spend on the additional lighting processing time. Finally, you can avoid those reflective materials. And PBR is great, but those super shiny metals aren't going to look so good in VR. So try and stick with your more matte materials, right? So there's a huge range of mitigations available for you guys. You want to try and do as many of them as possible. So going back to the original 4, aliasing, there's lots of things available. Try it all out. See what works best for you. If you find one of them isn't working great, just stick with what you got. Make sure you play around with texture filtering a lot. It's going to take a while, and you'll definitely get varying results. But when you get it right, you'll get a good performance to quality trade-off, which is what you want. Banding, it's really hard to remove. Yeah, we all know this. So you need to try and work on those mitigations, but also try to design your levels to avoid having those banding. Avoid places where it's going to occur, right? Don't get those dark scenes with lights nearby, because then you're just going to get banding straight away. Shadows, they're vital for immersion, and those blob shadows provide a good middle ground between really fancy shadows, but also paying on the performance processing side of it, right? So all of these mitigations work great, and you need to think about it, but also design your game considerate of the weaknesses available or present in VR, right? So thank you very much. At the end, I've got some resources for you here. So at the top, there's a lot more tips in this VR guide available at the top link. And then there's a blog post I've written on the second one to give you some more information about the guide, and that has a link to find the rest of it. So the guide has lots of exactly how to do step-by-step, how to implement this stuff in Unity with screenshots to help you guys. And at the bottom, we've got the ARM developer Unity page to help you out with all the things for deploying on ARM GPUs, of which there's lots of. So thank you very much for your time, and enjoy the rest of the conference.